I can start talking a bit about the structure of the talk, though. So the plan is generally that I want to show a kind of motivating toy example of a common performance pitfall that people encounter with Julia, which is okay. So I want to show a motivating example of a common pitfall that people encounter with Julia code. And then I'm going to talk a bit about what exactly is this term that people throw around, which is heap allocation. And I'm going to talk about stack allocation and how that differs from heaps. And then I'm going to talk about a package I've been working on called Bumper and how it can try and help you take control over these situations where, specifically where allocations are causing intermediate allocations in the middle of a program are causing problems for you. So here's kind of a more or less classic problem that someone might show on discourse or something. Why is my function slow? So they have some outer function that's calling some inner function in a loop many, many times. And if this inner function is going to allocate memory, you're going to get n allocations. And what people will tell you right away is don't reallocate that memory all the time. You should be pre-allocating some memory outside of this loop and then be modifying that memory in place as you go. And so what's kind of frustrating about this is, I mean, first of all, can the compiler please do it, blah, 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 but also just, this isn't always practical, because say I'm the writer of the inner function, but not the outer function, or I'm the writer of the outer function, but not the inner function, then I can't always coordinate this process of putting some temporary variables or pre-allocated slabs outside of this function that the inner function calls and modifies in place. And this gets worse and worse, the more different temporary variables or temporary allocations this inner function is going to be creating. So if you have 20 different things in there, you're going to have 20 different buffers, maybe with different types and stuff that you're modifying in place. Okay, so if we take a step back and just ask, okay, say I'm new, what's an allocation anyways? And why are there different types of allocations? So let's make a little toy model. This is a mutable struct. I'm calling it box. It can hold one item of type T. And this thing is mutable in the sense that you can create it with some contents and then change those contents and get out a different number when you access it again. And now let's compare two different functions. One of them is going to be called makeBox. This just creates a box storing the number 1. And the other function is going to be called make and openBox. First, it calls makeBox. So it's just making a box storing the number 1. It asks the compiler to not delete this box, please. And then it returns the box. It returns the contents of the box. And if we look at a benchmark of this function, first makeBox, we get some distribution of timings that can range from 4 to almost 400 nanoseconds. The vast majority of these times are going to be around 5 nanoseconds with some variation. This is actually very fast for a heap allocation. This is good, but things aren't always so happy. But if we compare that to make and openBox, something perhaps unexpected happens, because this function, which calls the first function, is faster. And not only is it faster, it's significantly more consistent, and it reports 0 allocations instead of 1 allocation. So that's a little mysterious. Why is making a box and opening it faster than making a box? And why doesn't it allocate? And yeah, so if we look back at these two functions, the main difference is that when you look at this definition, just make box, you're just creating this box and pushing it out into the world. Whoever calls this thing is now the owner of that data. and it's their job to determine, or it's up to them how long this thing lives. From the point of view of Make and OpenBox, this is one of those consumers. Make and OpenBox creates a box, but then no one else is able to see or access this box once the function continues. And so it's able to use this finite known, statically known lifetime of this box to perform optimizations that make this thing faster than just the sum of its parts. So even though we asked it not to delete the box, it knows it has a finite lifetime. And something that I didn't know until maybe too recently is that it's actually really fast to allocate data in general. Allocations are not slow. It's making allocations that can be deallocated at some arbitrary time later that takes a lot of time, and that can cause us problems. So heap allocations are generally what we have to do when we don't know when an allocation is going to, like how long it's going to live. And so we have in Julia a system called a garbage collector, and this sets aside space for these objects, and it keeps track of when they're in use. And so when you create an object, you have to notify the garbage collector, I'm creating an object, give me some memory, and mark this region of memory as in use. Then periodically, as the program runs, there's going to be some sort of non-deterministic thing that happens where every once in a while it'll be like, okay, you've done too many of these allocations. I need to go through, I'm running low on space, I need to go through all the tracked objects and figure out, okay, this thing is not in use, this thing's not in use, this thing's not in use, and I can delete these. And hopefully I'm not butchering this, but basically this is generally the time-consuming part of this process. And I guess the other thing that's worth noting is that this process requires access to the Julia runtime. So if you're interested in using static compiler or other things where you're running without access to Julia's runtime, then any process that does a heap allocation is a no-go. The other kind of species of allocations that people encounter in Julia are called stack allocations. And these are often kind of thought of as magically different. The basic thing, though, is that Julia has something called a call stack, where it stores the addresses of every function that you go through. So as you execute some program, you're going to put the addresses of the functions that you're in on this call stack, and so that you can have good error messages and things like this. Most programming languages have one of these, but something that's somewhat common is actually storing data on this call stack, because you could store whatever you want on it. It's some buffer of memory that's available to the program, so you might as well stick data on it if that's okay. And what's nice about this is that, generally it doesn't require access to the Julia runtime because the call stack already exists. It's embedded in the LLVM code, essentially. So static compiler can use this. And stacks are really simple. So it's just some slab of pre-allocated memory created at the start of the program and an offset, or generally at the start of the task creation. So this offset is just some integer that tells you where you are on the stack at a given point in the program. And putting memory on the stack is so cheap that benchmark tools or profilers and stuff do not report these as allocations. We don't even consider these things to be allocations. So here's a little example program of what at least an idealized version of the call stack might look like as we execute the program. So we enter this function f, and we're going to put f onto our call stack. And then we set our offset one position to the right of f. Then we enter this function g, and so we put g on the call stack, and we add 1 to the position. We enter the g function where we're doing plus, so we put plus on the call stack. Once that returns, we can move all the way back here because these functions are done executing. Next, we want to create a box, and if this box gets stack allocated, it's say going to take up 2 positions on this stack because it's as wide as 2 of these function addresses. So we move the position over a couple points to the right to allocate our container, then we enter H, then we enter minus, and then H finishes, we move the stack back, and then, I guess I'm missing a slide here, but basically, after H is done and we no longer need B, then we can move this stack position over. So the process of doing this is just integer addition and subtraction, or saving an integer and resetting the offset. So if you need to create space on the stack, you need to reserve space for some other caller, then or someone requests some space, you just increment this offset and say you own the pointer from here to there. And then if you're now done executing this function, now you say anyone who has any stack space no longer owns this, I'm moving the offset back. So you can just reset the offset. So if this is so great and efficient, and people when they're trying to optimize problems really like stack allocations, so why don't we always take advantage of these allocations? One potential problem is that this process is an optimization. And so it's up to the compiler to turn your allocations into stack allocations. Stack allocations and heap allocations are not a semantic part of the language. They're things that occur as a part of the implementation. And so whether or not that occurs in certain edge cases can be really unpredictable. It can depend on other things happening in other parts of the program. If the compiler gives up optimizing something, or it can't prove that this box never escapes the function, then you don't get a stack allocation. And that's probably a good thing, because if you demand that you get some stack allocation and then that thing escapes the function body, then you can get basically something called read after free, where you have invalid data floating around in your system, and this is memory unsafe. The other thing is that stack allocations, like whether or not how this happens, is tied to function inlining, and so you could get something called a stack overflow, where if you inline some big function that takes up a bunch of space and does a bunch of other stack allocations, you could actually blow the call stack and cause an error in the middle of your program. So Julia does a lot to try and avoid you causing a stack overflow in this way. And one of the things that it does to avoid that is it doesn't allow you currently to do a dynamically sized stack allocation. So we only do stack allocations for objects where you can reserve the amount of space you need based off just the type signature. So, so this precludes arrays, and this is the main reason people like static arrays, but it's often kind of annoying to over-specialize your code on the size of every allocation just because you want some space on the stack. So what can we do about this situation? One option is just to jump through hoops until the compiler optimizes whatever you want. You use static arrays, you write a bunch of generated functions to unroll everything, and then play whack-a-mole with the optimizer until it obeys you. This works really well until it doesn't. Generally, it works really well during prototyping, and then you set your code aside for a couple of years, you download a new package, you use a different version of Julia or something, and suddenly your optimizations go away, and you have to rethink what you were doing, and people tell you, well, you shouldn't have done that in the first place. The often preferred solution is to just pre-allocate objects like we talked about at the very beginning. This is great when it works. It's annoying, it's ugly, and it's not always practical. So I guess, so the genesis of this package then is, if the stack is so simple, can't we just make our own? Like, do we really need Julia's call stack specifically? And the answer is no, not really. Most of the time, we don't actually need Julia's call stack. We can just make our own call stack, and we can do our own unsafe stuff on it if we decide we want to. So here's a benchmark using arrays. So I guess there's a typo in here, but basically this is just a benchmark of allocating a vector of ones and then summing it. And I guess the thing to know is that this is taking, from 30 to 400 nanoseconds and stuff like that. That can depend on my computer, but it's probably from the garbage collector. But what we know is that this ones, this dynamically sized vector here, is a temporary array that doesn't actually need to be reallocated at every iteration of the loop. And so we can rewrite this function for bumper, and it's going to look like this. So we write some function f. Ideally, it takes a buffer as a second argument, and we mark the start of some region with this no escape macro. This marks a checkpoint in our program, the start. Then we allocate a vector. This is going to have n elements. This is dynamically sized in general. And we're saying it has the L type 1. I'm going to assign each element of this vector the number 1, and then sum it up. And then at the end of this block, what bumper does is it resets the buffer to its original position. So if we used a very simple buffer that works just like Julia's call stack, this would just be storing the offset at this position and then putting that offset back in at the end. And ideally, this can be a lot faster than doing intermediate heap allocations, both in the sense that you don't have to wait for the garbage collector to put aside space for you, but also that there's much less variation and latency implications from having the garbage collector unpredictably run in the middle of your program. So in this sample of 10,000 samples, 998 samples evaluations per sample, the longest running run I got was 27 nanoseconds. And I got a mean of 14.8 plus or minus 5, or 0.5 nanoseconds. So this is a much more consistent performance characteristic. If I vary this by array length and run this benchmark many times, these dots represent individual benchmark runs, and the lines represent the medians. You could do the minimum if you prefer. It doesn't look very appreciably different, but this line would go through the bottom here. And keep in mind, this is on a log scale, so this gap is actually a pretty appreciable amount of time here. We see that there are distinct advantages to eliminating these intermediate allocations, basically. And so if we actually look at what is the speed up factor for this kind of benchmark that's designed to favor bumper, we're getting like 2 to 7 times speed ups, which is pretty nice. So what's actually going on when you write one of these blocks is you create a checkpoint on this buffer that stores whatever data it needs to store to later reset, and then it runs your code. It does this in-place modification of this buffer argument, and then returns whatever your function does, binds that to some result, calls this checkpoint restore function, which resets your buffer to whatever initial state it was in, and then gives you your result. So what's nice about this is that you can define your own allocator types that make their own trade-offs that are separate from the ones that Bumper is making. So all you need to do is implement this interface of 3 or 4 functions, so checkpoint save, checkpoint restore, and then either alloc pointer or alloc. So alloc pointer should return a pointer if it's given a number of bytes, or alloc should take in a type, a buffer, and a size, and give an array. And so you can make your own allocators with these 3 or 4 functions. So Bumper out of the box has 2 different allocators. One of them is called alloc buffer, and this is just like a regular call stack in a language like Julia. So all it does is it stores some single chunk of memory in an offset, like we talked about. This has the advantage that it's just as fast as stack allocation because it's doing the exact same thing. It's very simple. It has very consistent performance characteristics because there's not really many different things it can do. The disadvantage of this is that it has a fixed amount of memory. So you have to decide when you create this buffer how much memory you're allocating to it, and if you run out, you're going to get an error. And so for that reason, this isn't the default, and this is not the buffer that I used for the benchmarks I showed before. The default buffer that we use is called slab buffer. You can think about this thing as like a collection of alloc buffers. So this is a strategy called slab allocation, where basically you have some slab of memory that you start off with. You do allocations on it. If you run out of room, you just make a new slab, and you make that one the active slab, and you push your other ones back in the queue. If someone asks for a super, super big allocation, you can make a custom-sized slab for that allocation. And that's why we saw in the previous slide, some of the later benchmark runs were getting less consistent for Bumper because it was running into these custom slabs. The advantage of this is that you can start small and dynamically grow your buffer. And the disadvantage is that it's typically, at least on my machine, a couple nanoseconds slower in the best of cases than the alloc buffers. And because it's more complicated, there are more things that can happen. So like if you're constantly crossing this threshold where you need to allocate a new slab, then you're going to have to pay that cost of allocating the slab each time. But the nice thing is that you can choose for your specific use case which one works best for you. So one thing that I complained about before is that when you're pre-allocating buffers, you don't always have control over the signatures of the functions that you're calling. So you can't always add an extra argument to your functions where someone's passing in a buffer. Or even if you can, maybe you don't want to because it's ugly. You might have to modify 20 different functions in some call stack to pass along this buffer. So we provide a function called default buffer. And this is kind of this accesses some task local storage. And the first time you call it, it's going to create a buffer and store that in the task local storage. By default, this is a slab buffer. And the next time you call it, it's going to give you back the exact same one you got the first time. To prevent you from running into problems with concurrency, we make it so that this is task local. So if you call a async task or like a multi-threaded task, you'll get a different buffer than the one you got before. So this one's false, but that one's true because this was on a different task. And what that means is that bump allocators that are running on different threads won't interfere with each other. The downside of this thing is that it does have a modest performance cost. On my machine, it was around 9 nanoseconds to access this task local storage and get you the buffer, but sometimes that's better than passing it around through every call. So what could go wrong with this approach? Turns out a lot. Bumper is creating and manipulating raw pointers. It's a relatively young package. It's written by one person. It doesn't have has a somewhat small test surface so far. So if there is a bug in Bumper, it would have nasty consequences for the correctness of your code. So a lot of testing has to go on if you want to use Bumper for something serious. So if you do decide to try out Bumper for some project, it would be really nice if you could submit a sample of what you're doing with it so that can be added to the tests. And so specifically, one problem here is that Bumper makes it your responsibility as the user to not let any allocations that happen in a block escape that block. And reasoning about that manually can be very hard and error prone. There's a reason that people don't like using memory unsafe languages and don't want user bugs to cause out-of-bounds errors. So I've been experimenting with Julia's built-in escape analysis in the compiler to try and help with this. I have some demos where it works, where it can work, but I can't currently throw an error at compile time in a regular function if your pointers are escaping. So that's something I would like to see evolve. Yep. Yes. So this is the conclusion. So basically, with these scary caveats made, the reason you might want to use Bumper is that you can take control of your allocations. You can have dynamically sized stack-like allocations, which is incredibly useful. And these will have very predictable and reliable performance characteristics. You can create custom allocators using this interface that suit your needs. We have one in static tools, for instance, that works totally fine on static compiler. We're kind of trying to move static compiler code to basically use this as its garbage collector. But everything has to be deterministically scoped. But you could have a custom allocator that does additional safety checks at the expense of speed. So for instance, this escape analysis version was a custom bumper. You could have some sort of verification mode that checks some sort of ID at creation. And you can make different performance trade-offs from the ones I made and plug that into this existing interface. Okay, thanks for listening.
Thank you. I think there's room for maybe one or two quick questions. We have one here at the front. I'll walk to you. It's very easiest.
So thanks for the talk. So are these allocated storages, are they regular Julia arrays and matrices or something else?
So it depends. With the alloc buffer, it can store any type that you put into it. So it's really up to you. That type just needs to support size and the pointer function. So it can store a vector, it can store a memory slab, whatever. The slab buffer is specifically calling malloc to get its slabs and then storing those in a vector. The version in static tools does something similar. It mallocs a pointer of pointers, and then it sometimes resizes those if it needs to, because I don't have access to vectors in static tools.
Maybe I can just add a little bit more. So the reason why I ask is like these allocated arrays or buffers, how do they interact with BLAS library, for example? Is it calling a specialized multiplication routines, or it fallbacks to a generic version which is maybe slower?
So what I use here, because wrapping a Julia array, if I bring my own pointer and wrap a Julia array, that still incurs an allocation, a heap allocation. And so I'm using pointerarrays.jl or stridearrays.jl. But if someone creates their own buffer type, they can have control over the type of the array that's created and has different characteristics.
I think Chris is really eager to ask a question, and that'll be the final one.
Yeah. Have you played around with using things like overlay tables to try to, at least within a context of a function, say, hey, can I take over automatically all of the allocations inside of here and make them all go onto a slab buffer? So that way someone who is the caller can do that to someone else's code?
Yeah, so I have played around with this. The tricky thing for me is proving that an allocation doesn't escape, because if I take someone's function, I do some cassette-like transformation. I take their function and turn their allocations into a alloc, and then they return that allocation. I've just done something very incorrect. So need good escape analysis to do that, but it's very possible, that you could tune someone's code, run the escape analysis, figure out which allocations don't escape, and then provide the pointers through Bumper.
Okay, thank you very much. I was told during the previous let's have a round of applause.